Alright guys, welcome to Statistics Chapter 3, Section 2. We're talking about measures of variation. So the main thing that we're going to be focusing on today is what's called a standard deviation. You probably heard that term before, but we're going to go over a real in-depth kind of what it is and what it is used for today. So first of all, a few terms. Range, this is a term that kind of gets thought of incorrectly because when we're in a stats context, range means a different thing than when we're in an algebra type context. So in algebra, it's like the possible outputs or y values, whereas here in a stats context, it is the difference between the largest and the smallest values. So we take our biggest number and our smallest number, we subtract them, and that tells us, hey, it's the distance between those, or the difference between them. Then variance and standard deviation, they're really measures of the same thing, so we kind of use them together. But you're going to see a standard deviation 99.9% of the time. But it comes from the variance, so that's why we kind of pair them together. And they're measures of how spread out our distribution is. So if you think about our classes in our histograms, right? If we have a massive spike right in the middle of our histogram where most of our data is really, really close to that center, that's going to be a very, very small standard deviation because there's not a lot of variance or spread from that middle point. If it's very, very wide and gradual and spread out, that's going to be a higher standard deviation because more of your values are further from that actual middle point. So in a visual way, that's kind of what it means. It's really a measure of how spread out or not spread out our data is. So this is a little bit intimidating, but this is effectively our process for finding the sample variance and the sample standard deviation. So I want to real quickly point out that, and you're going to see this all year long, for some reason PowerPoint has a hard time putting the full bar over the x if it's in an equation. It looks just fine when I put it in on my computer and the previous screen, but when I actually present it, it hides it. So you're going to see a very, very small dot there and there. Those are actually x bars, not just x's with a weird dot, so let's kind of keep that in mind. So anywho, first thing that we want to find is the x bar, or the mean of that sample. We've gone over that in the past. Add up all of the values and then divide by how many of them there are. There's your sample mean. Not too bad. Then what we're going to do is find the deviation of each individual thing from our mean. So what that means is if you see just the x and no bars on it, that is an individual sample, right? So it's a response that I got from one object. So let's say I'm measuring heights, right? And my average height is 5'6", and this one sample that I take is 5'8". I would do 5'8" minus the 5'6" as my average, and I would get 2 inches as my deviation there. And you're going to do that for literally every single point in your data set. So if like you have 30 different things from your sample, you take all 30 and one at a time. That sample minus the average. That sample minus the average. You do that for every single one of those. Once you've done, we want to square them. So we're to take them to the second power. The reason why we do that is so that everything turns positive. Because if we're just taking the difference here of x minus x bar, we're going to get some of them negative and some of them positive, and in general it'll kind of balance out to mostly 0 most of the time, which is not going to be very helpful. If we then take those and then square them, now they are all positive. So once they're all positive, now we can add them all up to find the sum of the squares of the differences. Okay, so this little summation symbol, we subtracted all of them, we then squared each of those, and now we're going to add all of them up. Right. So for my example, I got 2 inches as my difference. I then would square that to 4 inches, and then I would add that up to all the other ones that I got from every other individual that I got data from. So that is effectively what we're doing. Now there's a shortcut way of calculating the exact same value, and that is this thing right over here. This looks a lot messier, but this is a lot easier to compute with the data you were given. To derive this into this takes quite a bit of work, so we're not going to do that here. But just trust me, you can get this from this. So once we have that, we effectively can get the sample variance. So the sample variance is the average of these values, right? So we just take this or this, and we're going to divide it by the number of samples minus 1. You would typically think of the average as being just the n. There's some really weird kind of technical reasons as to why we need to do n minus 1. We'll get into that a little bit, like chapter 8 or chapter 9. But for right now, just trust me, we have to divide by n minus 1 and n not n. So effectively averaging these, so we add them all up and then divide by n minus 1 in this case, and we get our sample variance. Our variable for sample variance is s to the second power. Okay, which feels like a really weird variable to get and use until you see, well, it's because we actually care about the standard deviation, which is just s. And how we get that is we literally square root the sample variance. So to get rid of the square on the s to the second, we square root it and we're left with just the s, which is our variable for standard deviation. So all these are literally just taking this and square rooting it. And now, I mentioned this, but you'll see two equations here. The top one is using this equation here, which is effectively a much easier way to see what's actually going on, whereas this is a much easier thing to compute. So we're probably going to be using this mathematically more, but this makes a lot more conceptual sense as to what I'm doing versus trying to explain that through this. So that's why I have both of those being shown. And those are kind of small, not necessarily super easy to read. Here's what you need. Okay, here's the 4 things you want to be able to have in your notes as a point of reference. So the defining formulas, this is going to make a lot more sense as to what it's actually doing, but the ones you're going to be actually using when you run a calculation are going to be these two over here. And out of variance and standard deviation, you're going to be using standard deviation drastically more than you're going to be using these sample variance. Honestly, if it wasn't effectively the same thing, but just one is being square rooted, we wouldn't even bother trying to find this, because this is just a much better, more efficient value to use to kind of judge the spread of a distribution. Okay, so let's try one of these out. So I gave you an extremely small sample size here. So it's just 6 values. And we're going to go through the process of computing this. So here is your x's. So then compute the x to the seconds. And then you can sum up all of your x's and then sum up all of your x to the seconds. And then use those to find the values over here. So go ahead and pause and do that and then come back. Okay, so you should end up getting this. So we get a mean of 6, and then we get an n minus 1 value of 5 because the n is 6. So then if we calculate the sample variance, which is going to be the s squared, we get 1.6. If we square root that to get our standard deviation, we get about 1.26. So that is effectively what you should be getting for that one. Okay, so what these tell us. So first of all, the range tells us the difference between the highest value and the lowest value. So it's kind of, hey, here's what the total spread of your data is. It's this long or this big or something along those lines there. Our sample standard deviation is effectively telling you how far from the average a certain amount of your data is, right? So if that value is very, very small, it's going to be a lot more data close to that average. And if it's very, very large, you're going to be a lot further from that average. So it'll be a lot more spread out. Your variance tells you the exact same thing as your standard deviation does. It's just not as widely used because it's a value that is a little bit harder to relate specifically to an amount of data, which is where we're going to kind of go next. Okay, so population parameters, these are effectively the same thing as we just did, but what we just did was for sample statistics. So the majority of the time you're going to have a sample as opposed to a population or a census. So that's why we kind of focus way more on like those. So all of these are effectively just alterations of what we just kind of covered, right? What you'll notice variable-wise, we change our x bar to a mu. We change our lowercase n to a capital N. We change our lowercase x to a capital X whenever we're talking about the entire population here. And then our S is now a sigma. And this is a sigma squared here for the variance and just a sigma for the standard deviation. The other thing you might notice is that for these two values here, it is just n, it is not n minus 1. You don't have to do that if you have a census, only when you have a sample there. So again, have those down, but you're not going to use those nearly as much as the ones for the sample standard deviation. Okay, so coefficient of variation, what this is just taking that standard deviation and trying to normalize it so that we can compare it to other things. So for instance, if I'm trying to get data on the average height of people, right? If I do that in the US, I will probably be using inches and feet. So my standard deviation will also be in feet/inches units, right? Whereas if I go to Europe or Asia or basically anywhere else, I'm going to be using probably centimeters to measure height. So that means that my standard deviation would be in centimeters. Now, my standard deviation in centimeters, I can't directly compare to a standard deviation that is in inches. So if I want to try and say, hey, which one has the wider spread, the larger standard deviation, I need to have a way to change those into equivalent values. And that's what the coefficient of variation really does for us. So we just take that sample standard deviation and we divide it by the sample mean. And then we're going to multiply that by 100% just to kind of get it to be a prettier value for us. And then now we have a the percentage of the value. Okay, so we're going to go ahead and try that out here. So I got you these values here. As opposed to having you try and calculate these by hand, I will go ahead and give you that the standard deviation is 0.62 and the x bar is 1.87. So use that and try and compute the coefficient of variation like we did there. And you should get 33.16%. So go ahead and pause, just double check and make sure that you can do that. Okay, so we're not going to do that a ton. I do want you to be able to do it, but it's not really going to be a focus for us in this section. So next thing that we want to cover is Chebyshev's theorem. So Chebyshev, it's very fun to say. It's a little bit hard, so go ahead and try and say it. But it's really a theorem that discusses how much data is within certain standard deviations of our mean. Okay, so the formula which we use for it is 1 minus 1 over k to the second. Okay, where k is the number of standard deviations from the mean. So if k is 2, then we're 2 standard deviations from the mean on both sides. So my little example here, right? If I plug in 2, I get 1 minus 1 over 2 to the second. That's 1 minus 1 over 4. So 1 minus a fourth is 3/4, also known as 75%. So what does that mean and why do I care? What that tells us is that 75% of our data is guaranteed to be within 2 standard deviations above or below the mean. So let's think back to that height, right? If my average height is 5'6", my standard deviation is 2 inches. Okay, that's not real data. I'm just making it up, right? Then that means that if I go up to 4 inches, so that's up to 5'10", and down to 4 inches, that's down to 5'2". I'm saying, hey, 75% of my data should be between 5'2" and 5'10". So that's what Chebyshev's theorem says. Now, if I increase that and make it 1 minus 1 over 3 to the second, right? Then I get 1 minus 1 over 9. So I get 8/9 right, or 0.88888. So that percent of my data is within 3 standard deviations. So I could take that, spread out even further on both sides. So this doesn't work when your k is 1, because then you just have 1 minus 1 is like 0, which isn't really helpful for us. So that's why I have this little qualifier of, hey, this k value has to be bigger than 1. It's kind of nice, and it's our introduction to kind of how we can figure out how much data should be within these different standard deviations. Okay, so let's go ahead and find what's called the Chebyshev interval, which is just going to be what I just did for like heights of 5'2" to 5'10". That's a Chebyshev interval for the fake data that I just made up, right? So if we want the Chebyshev interval that contains 88.9% of the data, we just kind of did that. That means 3 standard deviations. What would that be if my mean is 525, my standard deviation is 30? So go ahead and try and figure out what's the lowest and highest value to make that interval that would hold 88.9% of the data. Okay, so we should know it's going to be 3 standard deviations like we just kind of mentioned. So if I go 90 above and 90 below, I end up getting 615 on my top end, 435 on my bottom end. So that's going to be my interval, which I know is going to have at least 88.9% of my total data in that interval. Okay, so that is it for 3.2. Here is our homework 1 through 4, and then 5 through 25, just the odds. And I will talk to you guys next time.